Hi, it's Julian Hall here from ARM. I'm going to talk to you this afternoon about the Trusted Services project. So I'll give you a little bit of background to start with. So this is a new project under the trustedfirmware.org group of projects, and trustedfirmware.org, in case you don't know, these are open governance community projects, and the intention is to provide reference implementations of secure world firmware for ARM v8A and M, and also to provide SOC developers and OEMs with reference code base that can be used to meet ARM specifications for the firmware. So the trusted service was first published to, it's a very new project. It was first published to trustedfirmware.org Git on the 26th of November last year. And it originates from work in ARM within the open source software group, firmware group, concerned with providing PSA services for Cortex-A. And so the idea is that it will help people to meet PSA certification requirements, but also hopefully go well beyond that in terms of making components for trusted services reusable. And I think it's fair to say it complements the existing trusted firmware projects quite well. And so we have TFA, which is concerned with secure boot, measured boot. We have Opti and HAF providing the sort of secure execution environments. And so this is more about the payloads for those environments, things that can actually do useful things to solve some of the secure service type problems that application developers will have. And so just to give you an idea of what trusted services are, it's a term that we've made up, and it's a general term that refers to sort of applications that perform very specific security related operations on behalf of clients. And so clients could be just user space applications, they could be kernel drivers, they could be other trusted services, they could be bootloaders, they could be quite diverse. But the important thing is that the service provider runs within some kind of secure processing environment. And the motivation behind that is to protect security sensitive assets from malicious software that might be running outside of that environment. And on Cortex-A devices, there's quite a diverse range of secure processing environments that can be used depending on SOC, depending on architecture version and on basic implementation choices. And so there could be secure partitions managed by a secure partition manager. They could run under a T, such as Opti, as trusted applications, or run on a secondary CPU in a secure enclave. So all of those are possibilities, and they all achieve similar sort of isolation goals. And examples of the sort of services you might run would be crypto. There's a PSA defines a crypto service which protects keys and provides a set of sort of primitive crypto operations that allows you not to expose the actual key material. A protected storage, maybe a firmware TPM running in one of these environments, or a UEFI key store. There's probably going to be many, many other types of services that could be classed as trusted services. Okay, so the work so far, this just gives you an idea of the actual reference environment that we've been developing these services in. And so this, we've been developing the crypto and the storage trusted services in conjunction with some extensions to Opti to provide SEL0 secure partitions. And so this is quite a complicated diagram that shows that. I don't want to go into many of the details of this, but this is, but so far, all of the trusted services that we've developed and tested have run in this particular environment. Okay. And so why have a separate trusted services project? Well, the Trusted Services project provides a home for service-related components that may be integrated and deployed in different process environments. And so that's really the main reason for this. I think from the earlier slides, it's evident there are quite a few choices that implementers have as to how to actually, where to run these sort of services. And the idea is one of the main ideas behind the project is to promote reuse and a level of standardization for service components that could be deployed in the different kinds of environments. And so because of that, the project is independent of any particular secure processing environment project. So for example, it's not tied to the OPTI project or the Hafnium project or any other project, but the way we've structured things should hopefully allow the services or the components to be put together and then deployed in those different environments. And so what we've tried to do is to adopt a common framework with standard conventions and solutions. We tried to promote component and test case reuse, and importantly for clients of these services, publishing standard interfaces. So independent of where the services are deployed, if you're writing an application that uses those services, it sees a common interface. And other benefits of this sort of thing is that by sharing components, when there are security enhancements, fixes, improvements, hopefully they're shared across different deployments. And things like having a common build and test solution, again, we can benefit from reuse in that area. So the end goal is that independent of what type of environment you're using in a product, there's a possibility of running the trusted services really in any of those environments. That's the real goal. Okay, so just drilling down a little bit more deeply into the goals behind the project. We set ourselves, a set of goals to actually try and really clarify what it was that we were trying to achieve. And this kind of summarizes those goals. So we wanted a project structure that made it easy to reuse components. We didn't want to tie potentially reusable components to any particular environment if it was unnecessary to do so. We wanted to make it easy for clients to consume interfaces. So these were interface definitions. So again, there's not it's not too cumbersome. There's not too much that you need to include to actually access one of these services. And to give us the reuse, we wanted to have a generic model, a generic layered model that allowed alternative layer implementations to coexist. So when you need to port a service implementation from one environment to another, it's a case of just interchanging maybe one lower layer from another, but higher layers remain consistent. We wanted to support service deployment into different processing environments. That was a pretty obvious requirement. We wanted to make it straightforward for you to be able to build and deploy the services in a diverse set of environments, and for that set of environments to be extensible. Testing, clearly these are security sensitive components, and so encouraging testing and building testing into the project early on was an important goal. And also to allow for testing in a native PC environment to help with development of services, but also to help with application developers who want to use these services. We've already seen how that was a smart decision, where we've done some work with other projects that, who want to integrate to the services. We were able to provide them with a PC-only implementation of a set of services, and it made the integration work very, very straightforward. And so I think that was a good decision that we made early on, and we're already seeing benefits from that. We also want to be able to reuse components from external projects, and to do that cleanly without having to maintain forks of those projects. So we set about setting up a structure that made that possible. And we also want to enable platform developers to be able to contribute any hardware-specific code where necessary. We didn't want this to be a project that is burdened with having to deal with porting different platforms. We wanted to enable the community to deal with contributing hardware-specific code in a straightforward way. And we wanted a build system that could deal with all of this and could integrate and to allow with integration with external OS build systems such as Yocto or Buildroot. So how we achieve that? Oh, I knew I'd do that overshot. Okay, so this slide, this is a little bit complicated, but I won't dwell too long on this one. But I just want to just give you an idea of how we've tried to handle sort of the reuse. And so this gives an idea of sort of the directory structure of the project. Just to introduce some of the concepts that we're using. And so starting on the left, we've got this idea of protocols. Protocols, if you're writing a client application, you want to use trusted services, the only place you need to go is the protocols. And we have the ambition for this actually to be a separate repo. And so this is where we have definitions of interfaces. And so these, again, are separated by layers on the operations, the parameter definitions of how you actually consume and talk to one of these service providers to access a service. That's what protocols is all about. External is about representing external components that we want to be able to include in builds of service instances. Tools, just about build tools mainly. Environments this is an abstraction that we've introduced for a secure processing environment. So we have one for secure partitions running under Opti. We have ones for running under Hafnium. We also have environments for native PC builds or builds for running in sort of an embedded ARM Linux environment. And so each of those is abstracted by an environment. The platforms is all about different hardware. And so where an environment needs to be extended with some hardware specifics, we introduce the concept of a platform to allow us to deal with any environment dependencies on devices, on drivers. That's what platforms is about. Components is kind of the interesting bit. This is where all the special code for trusted services lives. And so these are components that can be pieced together to create a deployment. And deployments are the things that define builds. And so we have deployments for the crypto service, for a protected store service, and for any other thing that you might want to build and deploy in a particular environment. So that's the overall project structure, and this structure is reflected in the directors in the projects. And if afterwards you want to sort of explore the Git repo, you'll see exactly the structure within the project. Okay, next slide. Just drilling down a little bit deeper into some of those concepts. So deployments, we've used this word to mean a build of something, whether it's a library, an ELF file, or whatever, that you want to be able to build to run in a particular environment. We're calling that a deployment. And so a deployment, for example, of the crypto service to run under Opti is a combination of this idea of a name, the descriptive name, and the environment you want to run in it. And there is a build that reflects exactly that, and will pull together external components, internal components, and produce a build that's suitable for that environment. And the idea is that the output of that can then be deployed to run under Opti or under whatever is the provider of the execution environment. Okay, so that's the concept behind deployments. And on the right, there's an example of a deployment. This is one that we use for running service level tests. So this is a deployment that runs under ARM Linux, runs in user space, and runs tests that behave like a normal sort of client of the trusted services and exercises the trusted services. So we treat any build as a deployment. Okay, the other important concept I just want to drill down a little bit more deeply is protocols, because this is going to be important to users of trusted services. And so, as I said earlier, the protocols define the public interface definitions, and the service and these are really split by layer. And so, what we call the service access protocol defines the set of operations supported by a service, and the per operation input and output parameters, and any service-specific status codes that might be returned. And we also allow for different underlying remote procedure call protocols. If a special one needs to be defined, then there's a space there under the protocols for doing that. And we have defined an RPC protocol to run over the FFA messaging that our reference implementation uses, but there's no reason why external protocol RPC standard RPC mechanisms couldn't be used either. Now, as I say, the protocol definitions are planned to be kept in a separate protocols repo. Currently, they're not, but we're planning to do that. And this is advice that we've got from other projects that's something that can really make access consuming the public interfaces by people writing applications as straightforward as possible. And currently, the structure we've adopted allows for different serializations for these protocols. And currently, we support two. We support Google protocol buffers, which provides a language-independent interface. And so that's great for people writing applications, for example, in non-C or C++ type languages, where there's a formal language-independent definition of the interface. And we also have a more lightweight C-type, call it PAC-C serialization, which is good for people writing C-type clients, maybe kernel drivers, and so there's less overhead involved there. But we've had interest from people using, looking at other serializations such as CBOR, and the framework we've got allows the number of serializations to be extended. Okay, so this slide is a general common layered model for what any trusted service looks like. And so it's a very simple model. So we view that there being really three basic layers with a peer-to-peer relationship between a client that will use a service and the service provider that implements the service. And it's the service provider that will be running in the some sort of secure execution environment. And so we've called the protocol that the client uses to access the service access protocol. And that should be the same independent of the environment that the service is deployed in and what underlying RPC protocol is used. Okay, the RPC is just about being able to invoke remote procedures, pass parameters, and return results. And again, we're kind of the higher layers are pretty agnostic as to what underlying RPC is used. And there's lots of flexibility as to what should be used there. And at the moment, as I say, we've only implemented a single RPC at the moment, but the structure would accommodate just about any conventional RPC protocol. And beneath that, there's the flexibility for an RPC to run over different messaging layers. And so this sort of common layered model is reflected in the project structure. And so it's really clear when you're looking at components, the components are concerned with the service layer or the RPC layer or the messaging layer. And so if you need to define new services or new RPCs, it's really clear within the project structure how you should do that. Okay, just a few words about test. So we've incorporated tests into the project right from day one. So it's such an important thing. We've got different classes of tests, and the number of classes is likely actually to extend. But currently, we've got tests we've got some unit tests, a few of these that run on very, very small units of code. We've got a lot of component tests that run at the component level within the components subtree within the project. And these are mainly tests that will run in a native PC environment. We have service tests, and these are really tests that represent how clients will use the services. These are end-to-end tests. And again, these can be run in a PC environment or on the real target deployments. And we also have a new class of tests that we've recently introduced called environment tests that really run within an execution environment, test any services provided by an environment. We've adopted CPP test for running our C and C++ type test cases. If you're not familiar with it, this is a fairly standard sort of XUnit test framework that supports the XUnit XML output format, which can be used for displaying results in Jenkins or whatever. So we've tried to use a very conventional approach for testing. And as I say, we've tried to make sure that as many tests as possible can be run in a PC environment to give you a very quick and convenient way of checking for regressions and for debugging certain components in that environment. And just a few words about where we're going. And so, the project has been running for several months now, but the next steps are really concerned with really moving from the reference environment we're in at the moment onto some real hardware. And so currently, when we're running on a real target, it's only been on an ARM virtual platform at the moment. And so one of the next steps is to actually replicate what we've done running on real hardware and to make sure our platform support model has been pipe cleaned. So it's going to be work to add new services. Currently, we've implemented the crypto and secure storage services, but there'll be work to actually extend the number of services we support. Hardening security, in particular, strengthening the idea of client identity and then implementing access control based on that. That's really quite an important sort of a hardening measure that we're working on. And in line with the PSA program, we're going to be looking to certify one or two platforms to actually to demonstrate that we have a viable approach that people can use to certify their own platform based on these components. And also, we're intending to extend the testing model to better represent real-life use case and also misuse cases to improve the security testing. And finally, if you want to find out more, here are some useful links, the link to the project itself, to the repos and documents, and to the mailing list. So that is the Trusted Services Project. Well, thank you very much for your time. I don't know if there are any questions. I haven't seen any. But yes, if you do think of any questions, please don't hesitate to message me or send me an email, and I'm quite happy to respond. So right, yes, thanks very much for your time. I think that's it.
Julian, thank you very much for your session, and to all those who attended, thank you. Mentioned he will be available in chat, and he's provided some great resources to learn more about trusted services. Thanks, everybody.
Okay.